Hello, everyone. Welcome back. So, today, I hope you had, well, first of all, I hope you had a wonderful long weekend. We had a short week this week. And some big news coming out. We are apparently going to be starting back at schools on June 1st, just on a voluntary basis, but to start. And yeah, that's kind of exciting. So, I'm hoping that I'll be able to see some of you folks back in class. If you want to join me, it's going to be kind of weird because I'm probably going to be doing a mix of both these videos and videos for the class like at the same time. So it's almost like you're gonna be watching a live session of me doing one of these. Should be interesting. Anyway, so that might become a thing, but I hope you had a great long weekend. And let's jump right into what we're covering today. So part three, linear functions unit. And we're covering parallel and perpendicular slopes. We have four main things we got to cover here. And the main gist of this is obviously parallel and perpendicular lines, which if you don't know what those actually mean or what a parallel line is, what a perpendicular line is, well, no worries, we're going to be covering that today. It's not like this gentleman here doing a really fancy parallel park there, which I wish I could do. Although I'm not sure how the driver examiner would appreciate that if you tried to pull that on an actual driver test, but it would be cool nonetheless. Okay, let's start with looking at parallel lines and slope and how they relate. And so let's suppose that you were running a race. Okay, you were running a race, you were driving a race, whichever way you want it, and you're running that race against your mortal enemy, whoever that may be. Maybe it's Donald Trump, maybe it's your mom, your dad, your brother, sister, who knows? But you're running a race against these folks, and we decided to plot your progress on this graph of your distance, so how much distance you're covering on the y-axis versus how much time you're taking on the x-axis, right? And this is the graph that we plotted. So we tracked your mortal enemy in the pink line here. We tracked you in the blue line. And the question I'm going to ask you is, do you think, based on how you've been progressing in this race right now, do you think you will ever catch up to your mortal enemy? So remember, your mortal enemy, he got a head start of, let's pretend this is 1 meter each square here. Your mortal enemy, he got a head start of 3 meters, right? 3 meters. You started at the point where there are 0 meters. So the question I'm going to ask you is, do you think that you will ever catch up? And why or why not? Well, for the folks who are saying, there's no way I'm going to catch up, why? Why do you think that you'll never catch up, just looking at this graph right here? Well, one thing that we need to notice here is that both of these lines are parallel. Both you and your mortal enemy have parallel, we can say parallel slopes or parallel lines. And what do we know about a slope again? What does a slope tell us? It's giving us some kind of way to measure what we call a rate, right? So this is the rate at which we're running, right? This is basically our speed. This is telling us what our speed is. It's our distance meters per minute. So meters per minute. And are we running any faster than our mortal enemy based on these lines? I mean, even looking at that, you don't even have to do any calculation on the slope. You can tell, no, we're running at the exact same rate. We are running at the exact same rate. And so what does that tell us about these lines? What does it tell us about these lines? If we go back to our, let's go back and recall, let's recall y equals mx plus b. So our slope-intercept form. Let's see if we can make some kind of very basic quantitative kind of analysis of what this is actually meaning right here. We have you and your mortal enemy here running a race, and we've seen that, hey, it doesn't look like we will ever catch them unless we get a little bit faster and our line tips a little bit steeper, right? So what can we say about this? Well, we've said that, hey, slopes, our m here, must be the same, must be equal, okay? Must be equal. X we don't really change, and Y we don't really change because those are they're just some point along either of those lines for our mortal enemy or for ourselves. What about B though? This doesn't necessarily have to be the same. This can be different. Can be different. And we can see that we do have a different B for each of these cases, right? Because the B, if we recall, it's our y-intercept. It's the point at which, in this case, we can think about where we started in terms of the starting point. So we were playing fair and square, and we started at 0 meters, but our mortal enemy, he got the upper hand on us, and he kind of tricked us, and he's starting 3 meters ahead of us already in this race, right? So this is representing kind of a different, we can think of it as a family of equations here, because we can have different b's. We can have different b's, right? So can be different based on the equation. Based on the equation. So let's say that, let's assume that that our mortal enemy ran at a rate of let's say what would be reasonable? I don't know. 30 meters per minute. Maybe that's really slow. And had a 3-meter head start. Represent that as an equation. So we're going to be assuming here that our mortal enemy ran at a rate that was linear, and his linear rate was 30 meters a minute, and he had 3-meter head start. So we have two pieces of information here. We have our rate, which we know rates are always going to be associated with slope of our y equals mx plus b, and we know that we started 3 meters ahead of us. And that, again, that 3 meters ahead is representing our b. So what would the equation of this be? Well, this would just be y equals, we said that 30 is going to be his rate, 30 times x, so 30x plus 3. So what about our rate? What would our rate be? What would our equation look like? So you could take a minute and pause the video and ask yourself the same question. What would our equation look like if we know that we were running at the same rate, but we started at a different point in time? What would our equation look like? Well, our equation, since we're running at the same rate, our slopes have to be the same here. Our slopes have to be the same, so 30x, but instead of plus 3, well, we're starting at plus 0. Or we can just say that this was just 30x, right? So you might notice something here in how we can define what a parallel line is, or how we can define parallel lines and slope. So let's make this a general note here. So a pair of equations, let's say of linear equations. Let's make this a bit more exact. Of linear equations. Let's go, instead of that run parallel to one another, we'll always have the exact same slope. We'll always have the exact same slope. We'll always have the exact same slope. And so I'll just do a little example here. So example, we could have a, so write an equation parallel to the following. Okay, write an equation that's parallel to the following. And let's say we have y equals 1 over 5x plus 6. Okay, well, the first things first is let's identify what the slope is. Slope equals 1 over 5. So our new equation must have a slope of 1 over 5, and it does not matter what the y-intercept is. So let's do the new equation over here. Y equals 1 over 5, and we want a different equation. We don't want the same one. So 1 over 5x, let's just do minus 10. Slope equals 1 over 5, and the y-intercepts here can be different. So different. And this is known as a family of equations, right? And we're saying that this is in the same family of equations because our slopes are the exact same, except we're starting at a different point on our y-intercept here. We're starting at a different point on the y-intercept. So let's make that a little point here. So this is an example of a family of linear equations. Since they share the same slope, but have different y-intercepts, And this was the same as the example that we saw above, right? Both of these both of these are a part of the same family of equations because they do have that same slope, but they're just starting at different points on that y-intercept, right? This one's at +3 on our y-intercept, and this one was at +0 on the y-intercept. There's not really +0, just 0 on our y-intercept, right? So these are a family. And it makes sense to say that they're a family, right? Because they look the same. They grow in the same rate. They have the same kind of general shape. They just start at different points on our graph. That's the best way to think of a family. And you could have a bunch of different families. You could have, let's say that we want to write an equation that was, there are three equations that were parallel to this one. We could write y equals 1 over 5x plus 0, y equals 1 over 5x plus 2, y equals 1 over 5x minus 2.74. All of those are included in the family of equations, okay? So let's square away this first one here and the second one. We're already halfway through. And we need to look at, well, if you're kind of wondering, well, we got parallel lines covered. Well, what about perpendicular lines, right? So perpendicular line. It's going to be the kind of, we can think of it as the opposite or the inverse of a parallel line. So we could say opposite or inverse. And when I say inverse, I'm going to pretend that we took that parallel line and we just made it intersect the other line directly at a 90-degree angle. So opposite or inverse of the parallel line. Okay. So, hey folks, sorry about the cut there. I was not satisfied with the way that I explained something, so I want to try and do it again. So we're looking at perpendicular lines here, and we're figuring out, well, hey, they're going to be the opposite or the kind of the inverse or the inverted version of a parallel line. And when we're talking about parallel lines that I've never touched, so remember up here we were saying that these parallel lines are never ever going to touch because they grow at the same rate. And perpendicular lines, they're going to touch somewhere. And down here we have a example of a perpendicular line, and we can get one piece of information about right away, right off the bat, what a perpendicular line is and how we can define it just looking at this graph. So let's look at this pink line as our kind of prime example here. Okay, let's look at the pink line as our prime example. And we can say, we can have an intuitive idea about what this pink line is in terms of its slope just by looking at it. Right? We see that it's going from a lower part in our left end to a higher part in the right end. What do we say if a line does that? Well, we say it has a positive slope. So we say that this one has a positive slope. So let's look at the blue line, the one that's perpendicular to this now, and let's think about, well, what's going on with that one? Because this one is growing. It's going from a high point, the left point, and to a lower point in the right side, right? So we can say just intuitively that this has a negative slope, right? It's going downwards. We can think of that as profits from day to day. If our profit started at day 0 over here and then it was day 5 over here, well then we've lost money, right? Because our line has gone down. Our line of money has gone down. So we have a negative slope. So we can say right now, but a perpendicular line is going to have a opposite sign of slope. Because we can look at this from two perspectives, right? We could say, well, what's the perpendicular line to this blue line? Well, since this blue line is going in the negative slope, its perpendicular line is going to be one that has a positive slope, so it's going to be positive. Or we can look at it from this way. This one has, what's a perpendicular line to this pink line? Well, it has to be a negative slope, right? Because it has to be opposite of this positive slope, so it's going to be negative. Great. So there's one stipulation. We have one more that we need to cover. And looking at this is the kind of hardest to wrap your head around. So what we're going to do is we've got to think about what is happening if we were to kind of follow this pink line. If we were to follow this pink line all the way up to the point where it starts to intersect this blue line. What's happening if we were to instead follow this blue line up here? How is the slope changing here? Because it's going drastically different, right? Instead of going positive, now we're going negative, and it's increasing much faster. So what's happening during that part? Well, let's look at what the slope of this pink line is. And the way we can do that, we can, instead of doing our slope formula, we can measure how many boxes this pink line goes across versus how much it goes up. And this is also called the rise over run. You might have remembered this from grade 9. So in this case, for our pink box, well, we see that it goes up 1 unit, and it goes over 1, 2, 3, 4, over 4 units. Well, so what? How does this relate to a perpendicular line? Well, remember, a perpendicular line is one that's going to run 90 degrees opposite to the other line. Remember, you could think of a perpendicular line as basically like a, if you were driving north and all of a sudden went directly east, this is perpendicular. That's a perpendicular line. And so what's happening though, as we, if you were to just suddenly go north, if you were traveling east, or if you were to suddenly go east, if you were traveling north, what does that look like? Well, let's see if we can see something that's happening here. So recall that we were going up 1 unit for this pink line and over 4 units. Well, what's going on with this blue line? Let's see. This blue line, let's do a different color. It's going, I'm going to use these 2 points for my point of reference. It's going to the left. It's going to the left 1 unit. So actually, let's put this over to the right. This is then our blue one's going over to the left 1 unit and up 4 units, right? 1, 2, 3, 4. And you might be able to see where I'm going with this. It's doing the opposite here, right? It's doing, instead of going up 1 unit, it's going up 4 units. And instead of going over 4 units, it's going over to the left of 1 unit. So it's going in the opposite direction. And it's going, instead of, it's taking the 4 units, and it's actually that it was going for its run, it's actually doing that on its going up. So if we were to actually measure the slope of what this is, the slope of this line over here, well, this would be rise over run. Well, it goes up 1 and it goes over 4 positive units. Well, the slope of this line over here, rise over run, well, what's the rise on this one? It's 4 units. But how much does it run over? -1 units, right? Because it's going in the negative direction. It's going in the negative direction over here. And so you might see that, hey, this is how it's related. Look, our rise over run of this one was 1 over 4, right? And for the perpendicular one, we flipped that fraction, right? Our 4 went on top, or 1 on the bottom, and then we made the whole thing negative. So -4 over 1, so -4 over 1, or just -4, whichever way you want to look at it. These two are equivalent. Doesn't matter where that negative is. You could put the negative, actually, the negative's probably better sitting out front, just right there. So we could say that for a perpendicular line, we have the slope inverts, or we can think of it as the fraction flips. So let's look through a few examples with this, just to get an idea of what's going on here. And then that'll be it for this video. Let me just pull these examples up really quick. Okay, I think we're on example 2. Example 2. So determine if the lines are parallel. So we're just going to go back to a quick example with that parallel line. And let's look at this one here. So we have 4x minus 5y plus 15 equals 0. And we have 8x minus 10y plus 30 equals 0. So with these ones, you're not going to know right away if they have the same slope. We need to convert to y equals mx plus b. We need to convert it to the slope-intercept form. So I'm going to call this 1. I'm going to call this one over here 2, and we'll do 1 first. So we have 4x minus 5y plus 15 equals 0. Let's start getting y on its own. So I'm going to move everything that's easiest to move right now. And actually, that might just be the 5y. Let's put the 5y on this side, the negative 5y. So we're going to do 4x plus 15. I'm going to add 5y, so plus 5y. And now we need to get y on its own, right? So we need to divide by 5. 5. And we have to do that for every term. So what we have is y. I'm just going to flip this so that my y is on this side. We have y equals 4 over 5x plus 3. So there's our first one. Let's do our second one here. And what's our second one? We're going to do it purple. And we had 8x minus 10y plus 30. Okay. Well, let's do the same thing. We need to get equals 0. We need to get y on its own, and I'm just gonna kick this 10y over here by adding 10y. So we got 8x plus 30 equals 10y. Well, we need y on its own, so we're gonna divide by 10. And what we're left with is y equals, what's 8 over 10? Well, that's the same thing as 4 over 5, right? We can divide all those by 2. X plus 3. And so are those parallel lines? Are those parallel lines? Well, yeah, they are, right? Because they have the same slope. So we could say, therefore, yes, parallel, because they share the same slope. And that's that one done. Let's think about this question here. Let's do example 3. Find an equation which is perpendicular to the following and another which is parallel. So let's say that we had the equation. Let's say that we had the equation of 7x plus 5y minus 5 equals 0. Okay. What I'm going to do, I'm actually going to put all this down onto a new page here. And we need to convert this to y equals mx plus b. We need to put this in y equals mx plus b. So first things first, let's move what we can. Right now, I'm going to do things a bit differently. Because this y over here is already positive. So what I'm going to do, I'm actually just going to kick everything over to this side. So what I'm going to do, I'm going to do 5y equals minus 7x. So I have to minus 7x plus 5. And now all I need to do is just get rid of that 5 there by dividing it. And we get y equals negative 7 over 5x plus 1. Okay. So now we need to create one that's parallel. So parallel. And one that is perpendicular. Let's start with the parallel one because that's usually the easier of the two to figure out. So parallel just has to have the same slope. And our slope in this case is negative 7 over 5. So how about we just do y equals negative 7 over 5x, and we can change the y-intercept to be whatever we want. Minus 27. That can be whatever you want there. There's going to be a variety of answers for that. And what about perpendicular? So flip sign on slope and invert the fraction. Invert the slope. So what would that look like? Well, that is going to be y equals, so it's going to be a positive fraction this time, but instead of negative 7 over 5, it's going to be positive 5 over 7. And then you can just leave the y-intercept. That doesn't have to change. That will always, you can change that y-intercept to whatever you want to be. It can be plus 7. This will always be perpendicular, as long as the slope is flipped in terms of its sign, and then you invert the slope itself. Okay. And we're going to do 2 more examples. Actually, 3 more here. Example, what are we on? 4. And let's say that we're given, actually, let's just do 2 more examples here. Given the slopes of 2 parallel lines, determine the unknown. And so for this one, let's say that we had, what do we need here? Let's say that our first slope, or m1, equals 6, and let's say that our m2, or slope number 2, equals a over 7, okay? A over 7. And we need to figure out what the value of a is, if both of these slopes are going to be parallel. So if they're both going to be parallel, remember, what is parallel? What's in common between parallel slopes? Where parallel slopes are the same, or in other words, m1 of 6 has to equal m2 of a over 7. So what if we set those equal to each other? Well, we get 6 equals a over 7, right? And now we just need to solve for a. We need to solve for a. So what's the way? Well, the 7 is being divided by a, so what if we multiply by 7? So times 7 times 7, what do we get? Well, we get 7 times 6 equals a, 42 equals a, and that's it. And finally, let's do one more example here. This will be 5. And instead of parallel, let's do perpendicular.
And let's get a question here. Okay, let's do A, or actually not A because we're only doing one anyways. Let's say that our first slope, m1, is -5, and our second slope, -2 over A. So this one we have to think about a little bit differently, right? We know that these two slopes are going to be perpendicular. We know that they're going to be perpendicular, and we need to figure out what A is going to be. Well, one way that we can think about this is we know for sure what one slope is, right? We know our first slope has a slope of -5. So what would be perpendicular to -5? Well, if it's perpendicular to -5, we need to flip the sign. So it's going to become positive, and then we're going to flip the slope itself. So remember, -5 would technically have a fraction underneath it, -5 over 1. So instead of -5, it would just become positive 1 over 5. And we know that this has to be equal to, must equal -2 over A, right? That's an A, not a 9. So let's set those equal to each other. So we'll do that over here. So we have 1 over 5, and I'll do this in a different color actually to keep things consistent. So we have 1 over 5 equals -2 over A. And you notice that a variable here that we need to solve for is in the denominator. It's kind of ugly. A trick that we can do is let's flip this fraction. But if we flip this fraction, we need to flip this fraction over here. So what I'm going to do, it's going to, instead of 1 over 5, it's going to become 5 over 1 equals -A over 2. And now we just need to solve for A. Just very similar to up here, right? Very similar to up here, or right here. So right now A is being divided by a -2. So let's multiply by -2 times -2. And then we do that on both sides, and what do we get? Well, we get -10 equals A, and that's it. Okay, so I will post some practice problems with this. I really hope this video isn't too long. There's a bunch of kind of stops and sputters there as I try and figure out a good way to explain this to you online. There are much easier ways to explain this to you if you're in class, but alas, here we are. So I will post a schedule for this week, and that is it, folks. Okay, have a good rest of your day. Bye.